Today's lesson will be about centripetal motion. Centripetal motion just describes a mass moving in a circle with a constant speed. So that means it's not going to speed up, it's not going to slow down, it's just constantly changing its direction. If you'd like to read up about it, you can go to the main class webpage. I believe the link would be found on March 18th. Click the supplemental reading package. Page 242 is when it starts. And you can do a little bit more reading up on that. But otherwise, I've got an animation here that walks you through basically what's happening here. So with centripetal motion, you have a mass that's just moving around and around in a circle. We assume this mass has a constant speed. It won't speed up, will not slow down. I use the term speed as the scalar because, as you can see, its velocity vector in the red is continually changing its direction. So even though the magnitude has not changed once, its direction is continuously changing, so therefore its velocity is continually changing. The blue arrow represents the radius to the center of the circle, or if you want, you can call that the displacement vector, because just like this little green mass, it's constantly moving into a new position. And so therefore, it's going to experience a displacement as well. So if I continue this on, and we're going to take a small snapshot in time. There we go, the animation stopped it there and there, so two small little snapshots in time. We'll call this our initial velocity VI when the green mass was right here. We'll call this point the final velocity when the green mass was moving there. And as you can see, their velocity vectors are slightly different. They have slightly different angles. Overall speed hasn't changed, so the magnitude of the vector is still the same. Likewise for our position vectors, so radius 1, it was sitting there, it's still the same distance away as radius 2, our final radius, but the overall positions have changed, and so therefore we have a change in position. So this is over a small little increment of time, we'll just call delta t, like the little animation says. So over that small little increment of time, we've changed from two different positions and have two different velocities. So typically when you have a difference in velocities, you do velocity subtraction. And so with that, you set up your vectors to represent vector subtraction. With our two velocity vectors, you connect the two tails together and just draw them off to the side like in the video here. You don't have to draw your radius vectors off to the side because they're already connected at the tails. So when you do velocity subtraction, if you have final velocity minus initial velocity, we start our resultant vector from the second and we point to the first vector. So it should draw them on, oh, wrong order. So it drew on the difference in position vectors first. So final minus initial, we'd start our resultant vector from initial, point to the final. Likewise over here, velocity vectors, final minus initial. We start with our vector at our initial and point to our final, and we have our change in velocity vector, and it should point towards the center of any circle. So this is where you get into a math lesson where you have similar isosceles triangles. So you have two sides that are identical here, and you have the short side at the end with a set angle here, and this little red triangle here is proportionate to this blue triangle here. So our two triangles have similar proportions, which basically means they can become a ratio. So that means the ratio of one of these long sides to its short side should be the same ratio as one of these long sides to its short side, and therefore we can make them equal to each other, because they will have the same ratio. That's handy because if we consider rearranging the terms, so that's such that now we have a velocity divided by our displacement or position, if you will, so the radius, multiplied by our overall change in our displacement, should be equal to the overall change in our velocity. Considering this is over a small increment of time, we factor that into our equation. If we do divide by time on both sides of the equation, it shouldn't actually change anything. So those technically just cancel out, but we're doing this to make a replacement. So if you remember that your velocity is defined by your change in displacement divided by your change in time, then we can replace this section right here with a velocity, and it looks like this. So now I have two velocities, and we can just group them together and they'll be squared. And if you remember, your change in velocity divided by your change in time is known as your acceleration. We can just do that quick little replacement. And this acceleration is explaining how the direction of our velocity vectors are changing. This is known as your centripetal acceleration. So V at this point is no longer considered a vector. When you square a vector, it becomes a scalar. So what we actually have here now is speed squared. The reason why it becomes when a vector is squared and turns into a scalar is something called the dot product, and that's a topic for a calculus lesson at a much later date. But for now, all you need to worry about is the fact that this is now a speed once it's squared. So that's the quick of it. I'll just stop this animation. And again, just want to remind you that your acceleration, centripetal acceleration, will always point towards the center of the circle. So what does that mean? Well, mathematically, you have a nice quick little equation now. So if I relate that to a question, so for instance, if you have a car and it's turning with a circular curve, so basically if you have a car that turns left or right down the road, it's going to have a little bit of centripetal motion. Think of yourself down the highway and there's a curve up ahead. Odds are good you're not going to take your cruise control off. It's going to have a constant speed as you go around a curve. You may not go around a complete circle, but you're still going to have a little bit of centripetal motion. In this little example question, just says a car turns a circular curve with a speed of 20 meters per second. If the radius of the curve is 100 meters, what is the centripetal acceleration? So your centripetal acceleration is just found by knowing two things, your speed and the radius of the curve. So if you arrange your equation, centripetal acceleration should be equal to your speed squared divided by your radius. Plug in your parameters, 20 squared divided by 100 should give you 400 meters squared per second squared. Don't forget you want to square both the units. Cancel off the square here with this meter down below, and you should have a centripetal acceleration of 4 meters per second squared. A lot of these problems aren't super difficult. It's just a little different. I have another question, well, coming up here in a moment. First, one other thing to note, calculating your centripetal speed. So when you're going around in a circle, it's handy to be able to calculate just the speed based on the time and the actual circumference of the circle. So if you remember your basic equation, if speed is or your velocity even, is your change in your displacement over your change in time, same thing you can be said about speed for the most part. Speed is your change in distance over your change in time. We're talking about going around a circle. So the perimeter of a circle, the distance all the way around a circle is known as the circumference, and your circumference is 2 pi times the radius of the circle. Now, I was quick about this and I drew more of a oval, but it's close enough. So if you substitute in the circumference for your change in distance, and remember that the time to make one complete cycle from Physical Science 20 should be known as your period, then you can create an equation for your centripetal speed to be 2 pi times the radius, all divided by your period to make one complete revolution. So it's very important that you remember that the time in your centripetal speed calculation is the period, not just any random time. It's the time to go around the circle once. So if you don't complete a full revolution, maybe you only go 1/4 of the revolution, then your period should be divided by 4. Or if maybe I gave you the time to go around 1/4 of that revolution, maybe it took 2 seconds to go from this point here to that point there, then you'd have to multiply that by 4 to get the full 8 seconds to go around the whole circle, and that's the time you would need for inside this equation. So we can now adjust your centripetal acceleration equation to include your period. So since your centripetal acceleration should involve your speed squared divided by your radius, we can rewrite that equation where you separate your speed square and your divide by your radius. If you turn it into 2 separate entities, so speed square multiplied by 1 over the radius is the same thing. If we put your equation for your centripetal speed in place of your speed square, it will look like this. So I've got 2 pi r divided by your period, it's squared. So if you factor in that square to each of those 4 terms, you end up with 4 pi square, which gives you around almost 40, about 39-ish. Multiplied by your radius square divided by your period square. So I've got a radius square in my numerator, I've got a radius in my denominator. You can cancel those, the square and the denominator out, and you're left with the equation, a different equation for your centripetal acceleration based on the radius of your curve and the period to go around 1 complete revolution, to be 4 pi squared times the radius divided by period square, or about 40-ish, 39 times your radius divided by your period square. But of course, use your calculator for that. And used in a question. So what is the centripetal acceleration of a stone being whirled around in a circle at the end of a 1.5 meter string on a smooth sheet of ice? So no friction, with a frequency of 1.25 hertz. So remember, with frequency, there's a inverse relationship with period, so we can substitute that in. So knowing what we're given, we have a radius of the circle, 1.5 meters. We have the frequency to be 1.25 hertz. So if you remember from Physical Science 20 last year, your frequency is equal to your 1 over your period, or your period is equal to 1 over frequency, whichever one works best for you. We can take the equation that we just went over. So your centripetal acceleration is 4 pi squared times your radius divided by your period square. We can directly replace. So if 1 over your period is equal to your frequency, then 1 over your period square should just be equal to your frequency square. You can just substitute that into the equation. And then you don't have to actually do this in a separate equation if you don't want. At that point, you would just plug in all your parameters. 4 pi squared, just plug that through your calculator, or 4 times pi, whatever you need to type it in as, times 1.5 meters, multiplied by 1.25. Now the units is a hertz, but a hertz is the equivalent of 1 over a second. So that's why I just have, I didn't write hertz this time, I just wrote down per second. And so in the end, once I factor this square through, I should have a meter per second square, which should give you about 93 meters per second square if you punch that through properly. So my next little video will talk about how that gets incorporated into forces. As I figure out how to stop the recording.